Welcome all of you for these lectures on fluid mechanics. Today we will discuss about fluid statics, that means fluid at rest. Before starting these lectures, again I want to repeat the reference books, like the most illustrations books like the Sinjal Simbala books, which is very good book in terms of lot of illustrations, the examples and the exercise what is given in Sinjal Simbala books. And who needs to very concise, they can read it, FM White book which gives mathematical forms with very classical problem solvings at exercise levels, also the in examples problems. And another books by Vidyasagar Pani on fluid mechanics is concise, which in Indian context book is very concise to read it. So please refer these reference books, the fluid mechanics, the fundamental and applications by Sinjal Simbala, or fluid mechanics FM White, or fluid mechanics by the Vidyasagar Pane. So these are what the reference books I have been following it. So please follow these books for additional knowledge on this fluid mechanics course. Now let us come to the contents of the today lectures. The first I will discuss what we so far in the last 3 lectures we discuss it. Then we will talk about concept of hydrostatics. Okay, that means the fluid at the rest. And most of the as you know it that when you consider a functions, okay, you can approximate the functions using a Taylor series. That the concept we will talk about. The Pascal law we will talk about. Then the major components like the pressure force on fluid element, that is what is the control volumes, that what we will also discuss it. Then we will discuss about what is a gauge pressure, what is a vapor pressures and hydrostatic pressure distributions. And there are 2 applications of these hydrostatic pressure distributions. One is barometers, another is a capillary effect. Then I will conclude today lectures by summarizing the lecture contents. Now let us recap it. As of now what we learnt it. We already know it, we talk about either a system approach or the control volume approach to solve the fluid mechanics problems. And whenever we solve the fluid mechanics problems, as I said it in the last class, we generally look for 3 fields: velocity field, pressure field and the density field. But when your fluid is incompressibles, then we just look for the pressure field and the velocity field. So these 2 fields we can get it using these 3 different approaches as I discussed earlier. One is experimental methods, conducting the experiment in a wind tunnels, computational approach which is a computational fluid dynamics now extensively used for a very complex fluid flow problems, or this analytical approach which is a very simplified problems we can solve analytically to get the gross approximations of these pressure field and the velocity field. So that is what we look at for the flow which is considered incompressible flow. And then we already discussed about that. To adopt these 3 different approaches, we have to follow integral approach, differential approach and the dimensional approaches. And very interesting examples what I have given it in the last class is that how the force, very complex flow fields, we get it in a radar tower due to this wind movement. That is what we discuss it that, and there is the option is there, we can do analytical solutions for that to get a velocity and pressure fields for a simple problems which can you solve it. And as again I can repeat it that the concept of the virtual fluid balls we discussed a lot, and that what will apply it when you go for fluid kinematics and the fluid dynamics part, which is later on I will discuss it that. And as a definitions already we said it that what is the streamline, the path line and the streak lines which is considered to define what type of flow is happening it, and understanding or visualizing the fluid flow problems, because that what using the streamlines, path line and the streak lines. Now, let us come to the very basic concept what we are talking about, the fluid at rest. So, the basically we are talking about now the fluid at rest. Okay. If it is a fluid is a rest, it is a very simplified problems now. Like as I said it, any fluid flow problems we look at either the pressure field, the velocity field or the density and temperature field. When the fluid is rest, now very simple way the velocity vectors becomes 0, and if I consider incompressible, the density is a constant, and if the temperature is not varying much, I need not need a thermodynamics first laws to define the problems, then only the left is that the pressure field. That means, when is a fluid is in rest conditions, only we need to know it how the pressure variations is going over this fluid domain. That is what our the simplified problems. Since there is no velocities, there is no velocity gradient, definitely as Newton's second law says that there is no velocity gradients, that means no shear stress. So, when a fluid is at rest, there is no shear stress acting on that. So, you can take a surface or take a control volumes, over that control surface you can define it, the shear stress components become 0. That is very simplified now. Any control volume you consider it, over that control volume surface, as the fluid is at rest conditions, there is no shear stress acting on the control surface. So, that is the very easy problems what we have now. And what the two forces we have? The gravity force and the force due to the pressure distribution. So, whatever the pressure distribution force is, that what is equate with the gravity force. Very simple things now. And since is a fluid is at the rest, so you can say that there is no mass flux is coming into the any control volumes or the momentum flux or no external work done it. So, this is what the simplified case. Like for example, if you take this dam which is 100-meter high and we have a reservoirs, let you consider this is what 90-meter height from the bottom. That is what the water levels is a 90-meter from the bottom, and you can understand it because of this in the reservoirs the fluid is at the rest conditions, and that rest condition exerting the pressures on this surface. So, there is a vertical surface, there is a inclined surface. So, we need to know it what is the fluid pressure is going to act on this stem, on this vertical surface and also the inclined surface. Based on this the pressure load, we can design the stem structure. That is what the examples for fluid at the rest. Similar way, if you have a oil tankers, so we need to know it what is the pressure, the fluid oils which are in a rest, how much of pressure is exerting on the wall of the tank. So, it is the problems what we use to design a tank, big reservoir tank or the natural reservoirs like a dam, we try to know it how much of pressure is going to act because of this fluid fluid is at rest conditions, and how much of pressure is occurring because of this pressure, and what is the pressure force is acting on that. Similar way, what is the force is going to act on that. So, that is the problems what will solve it. Second thing is that fluid act as a rigid body motions. Let us take a examples here that I have a tank which is a half filled liquid is there. Let us consider it may have water, and this tank is accelerated with a constant accelerations a. As you start accelerating this tank with a constant accelerations a, you can understand it, this free surface is going to change it and coming to a equilibrium surface such a way that after that this surface will not change it. That means at that time these control volumes is moving as a rigid body and traveling with a constant accelerations of a. So, we can consider is a very simplified case now that these fluid control volumes what we have here, which is moving with a constant accelerations a and with these free surfaces, and that what will be there, and as it is moving it, there is no velocity gradient. So, no shear stress. So, we can adopt the hydrostatics concept. So, let me summarize what I am talking it to you, that one case we have the gravity dams where we know the fluid is at the rest. That means only the pressure force is going to act on the surface of the dam. In that case, we can understand it that there is no velocities, no shear stress, only the pressures what is going to act it. But in case when you have a rigid body motion, the fluids work as a rigid body motions, like the tank is moving with a constant accelerations of a. The similar conditions can be considered it any liquid filled containers moving with a constant accelerations a, and what could be the free surface, what could be the height of the free surface, all we can compute it, that what in a later on I will tell it. But in conceptually, in this case what it happens is the control volumes moves at a constant accelerations. Because of that, there is no velocity gradients, as that of that there is no shear stress acting it. So, we can apply the hydrostatic concepts. So, one case there is no velocity field at all because fluid is rest. Another case we have a no velocity gradient. So, that is the reason there is no shear stress. So, we can apply the hydrostatic conditions, that the as equivalent to fluid at the rest conditions. Now, whenever I am talking about that, I am looking for a pressure field as the fluid is a rest. So, basically I am looking at the pressure is a function of the positions x, y and z. Time is not there as the fluid is the rest conditions. So, many of the times when you consider the pressure field, you try to look it from one point to other point, what is that value could be. Okay. Like for examples, if I take a very renowned series like a Taylor series for one independent variables, that means here the u is only a functions of x, only the function of the x, and u is the variables. And we know what is the value at the xi, the ui value, we know that. We want to compute it, what could be the value u I plus y, which is a delta x distance from xi, and that was xi plus 1. So, this is a known to us, when to compute what could be value u I plus 1, which is having a on the x direction a distance of the delta x. The Taylor series gives a infinite series, like if you look at ui plus 1 will be ui, that means at the xi locations, then ui dash, that means a first gradient of the partial derivative of u delta u by delta x by 1 factorials, then it comes to be second gradient, which is the del square u by del s square, then third, like this we will have a infinite series we can have. But most of the times what we look at in a fluid flow problems, we need not need these higher order terms. This is what the higher order terms. Okay. We need not need it, because these values will be much smaller than this the first term. So, we neglect this higher order term, only we consider this part. Okay. That is what. So, this is the higher order terms which are much less than these points, as you can see that delta s square is there, delta s q is there, and this value becomes much smaller as we go for more higher orders. So, we neglect that part, only we consider any functions if I am approximating at u plus I locations, that what will be ui, the first gradient of del u by del x by this value. That is what I am to say that. So, we can approximate either a pressure field, the scalar component of velocity field, or the density if it is we are considering as a the variable in a space and the time component like independent variable of x and y or z or the t. We can define them in a Taylor series very simple way as if yi at a one point yi plus 1 will be the first gradient into delta x. This is what we consider. This is what we neglected. This is what we neglected because these terms are very less as compared to the first term. But when you consider two independent variables, okay, that means the pressure is a function of x and y. For example, in that case, we can have the Taylor series in similar way. If you can see it that there we will have a I and j because ith will be in x direction, z will be in the y directions, y axis directions. So, yij will be again the first order terms of x directions and the y direction. Then again second order term which will be the in x direction and y directions like this we go it. As I already told it, these terms are much lesser because delta x squares we have, delta x cube is there which value as it a square, as it a small value, this becomes very less. So, whenever you consider two independent variable case, we approximate the function of at u I plus 1 and j plus 1 considering y u I plus j the component of the gradient component into delta x plus the second gradient component into delta y. That what we consider when we are applying the Taylor series to approximate a functions if I know at initial conditions and the next conditions which is a delta x or delta y from that positions. We can approximate the functions like this. If you are more interested on Taylor series, you can read any mathematical books to know how the Taylor series used for approximating the functions. Now, let us come it to very basic law which is called Pascal law. As when your fluid is at rest, let us consider is that there will be a normal stress acting on any plane. Okay, that is what we are considering is that what is the fluid pressure. Here I am considering a fluid element or you can say it the fluid control volume element or fluid control volume. Now, if you consider this is what my control volumes and along this perpendicular to this surface that is what my unit value. That means one unit I have considered perpendicular, this is a 3-dimensional control volumes. I am representing as a 2-dimensional things and I am defining the pressure Px is acting on this surface, the Pz is acting on this surface and Pn is normal pressure components acting on this inclined surface and each one is a delta x, delta z and delta x. So, if it is that when the fluid is rest, we can find out some of the forces acting on this control volume should equal to 0. So, then we can look at force in a scalar component in a x direction and the y direction. That means, the force component in x direction should be equal to 0, force component in the z direction should equal to 0. The force is what? The pressure into the area. As I said it, the pressure will be the pressure multiplications of area, that what we have done it and here we have considered B is a unit width, okay, not the unit width, we have considered it. So, you can find out the Fx directions, the pressure in Px into area, Pn and B into delta x sin theta, as you can obtain it the delta x part which will be sin theta component of the Pn, that what in the Pn sin theta component will act on that. So, we will have this equation. Similar way we can write equations in the z directions where you can look at there is a weight component on that. The weight of this element or the control volume will be half of B delta x by delta z, that is what the volume into multiplied with a unit weight which is rho times of g. This is very simple things. What is the weight of these control volumes will be the volume multiplications of unit weight, that is the multiplications of density and acceleration due to the gravity. So, you get the element weight, that the components, if you can see it, that components are here, and we have the force component what we have resolved. So, we have just considered this fluid element or the control volumes at the equilibrium conditions. That means the force is equal to 0, the force scalar component in x direction, z direction is 0, and we resolved the pressure into the force component, and that what in x and z direction. That is what we have done it, not much things different. But if you just rearrange this and cancel it, the first equations of these ones will give it Px will be the Pn. That means the pressure in the x directions will be equal to the Pn. Similar way, the Pz will be Pn plus half rho g delta x. If delta z is tends to 0, that means this component becomes 0. That means what you are considering is that your control volume become smaller and smaller, and it could be infinitely smaller values. Okay. That what you, if you consider it z equal to 0, then these components become 0. So, what will get it? The Px, Pz is equal to Pn. That means the pressure in the x direction, z direction, and the any direction of normal to the surface will be the same. Okay. That is what is the Pascal's law. That is what the Pascal's law. And since pressure is the same in all the directions, so we can consider is a pressure is a scalar quantity, and that what demonstrated by Pascal's law. Very simple way, as I consider it a fluid element, fluid at the rest conditions, and just equate the pressure due to the pressure, the force component and also the gravity component, equate in x direction and y direction, and consider that delta z tends to the 0. That means your control volumes become a smaller and smaller and infinitely smaller. At that periods, you will have a Px, Pz and Pn's are equal. That is the Pascal law. The mathematically we told its pressure becomes in a fluid rest conditions is a scalar quantity. The fluid flow what we are considering here, all the cases the pressure is a scalar quantity. That is what the Pascal's law. Now, if I go for the next ones, that how to get the pressure field when fluid is at the rest. That means I am just looking the what could be the functions of the P, which will be functions of P, x, y, z. If it's that, it is now again I am considering a very simple case. Let us consider a contour volumes like this. Okay, this is what my contour volumes. As I said it, when the fluid is at rest, the shear stress becomes 0. So, there is no shear stress component on this fluid plate. Only this normal stress, which is as equivalent to the pressure, will act over this control surface. Over the control surface, only the pressure is going to act it, because the shear stress is 0. Okay, that is very simplified case. And as you have considered is a simple parallel control volumes with having a delta x, delta y and delta z. There are 3 Cartesian directions of x, y and z directions, and I am considering a point which is just a centroid of the parallel is a this thing. At that point the gravity force is acting it, which is the body force component. The gravity force what will be there? It will be the unit weight multiplications of the volume of the control volumes, which is the delta x, delta y, delta z, and the unit weight. So, we can have a 2 force components. One is the surface force component, another is body force. The body force components, if you look at that, it will be unit weight multiply the volume of the control volume, which is delta x, delta y, delta z. That is very simple things. The control volumes, the volume is this much, and the unit weight is rho into g, and rho is stands for here the density and g stands for accelerations due to gravity. Now, if you look at over this control volume, all this pressure is going to act it as the Pascal law says that pressure acts normal to the surface. So, that what we can consider pressure acts there normal to the surface. Then we need to define now as a pressure as a x, y, z is a pressure field what we are looking at, which is a function of x, y, z. I can use of Taylor series to approximate delta y by 2 distance of this surface which is a far away from delta y by 2. That what is the first order approximation of Taylor series. This is what the Taylor series expressions, as you can see it what we discussed. This is what the Taylor series expressions. If I know P x y z, what will be the pressure at this y minus delta u by 2 will have a these functions. You can look at this negative part is there, because this is what delta y by 2 distance far away or negative side of or the opposite of the y direction. So, that the delta y by 2 will be there and we have a expressions like this. Now, I neglect this component. This is what we are neglecting, all this higher component here. So, it is a simplified to like this term. If this is the pressure is acting on this surface, similar way I can get it what will be pressure is acting in this. I know this pressure multiply the area over these simplified control volumes, I will get the force component. That what is acting along the y directions. That what if you equate it finally we will get these ones. The gradient and the volume of the control volume. The gradient, the negative gradient and the volume of control volumes what we will get it. This is the force component acting along the y directions. More detailed derivations of these simplified cases, please refer to web course what I developed a long back on NPTEL's. That is a link what is available here. So, that is what please go through that. So, what I am talking about that the force components acting along the y directions because of the pressures we can get it as a pressure gradient and delta x by delta y delta z which is the volume of control volume. So, similar way we can derive the pressure component the force component due to the pressures in x directions and the z directions respectively. If I do that, that what as a vector form I can write it this way. This is the force component along the x directions, this is the force component along the y direction, this is the force component acting in the z direction. So, this is the gradient vector. So, I can have a gradient vector field of df. As I said it earlier, only two forces is there, one is a gravity force and another is force due to pressure distributions. So, total force actings we can equate it df to dy, that what in terms of vectors we will have this minus gradient and delta rho g. As the fluid is rest, the sum of the force should be equal to 0, that the vectoricals is equal to 0 and that field what we will get it this part and which finally the gradient of rho and g. So, here please note it that we have not considered the x, y, z in any g can be any directions, g can have a vector. Okay, g not necessarily the g should be the just opposite of the z directions. Here we have considered g can be any directions, like you are solving a problems where the control volume you have considered very complex control volumes, your g may not exactly match with a z directions, then you can use as a vector and you can solve these problems with a gradient of phi will be equal to rho g vectors. So, this is the in a vector forms the hydrostatic equations which will be simplified in later on, which is very simplified case what you will get it in later on, but the general equations is these ones. The the gradient operator of P is equal to rho g, g is here the vector component of acceleration due to gravity. Now, the point is what we are going to discuss is that gauge pressure and vacuum pressures. Components now is coming what is your datum to measure the pressure? Whether you have to make a absolute zero pressures, that means you have a vacuum, from there you are measuring the pressures, or you consider as a local atmosphere to measure the pressure. There is two conditions from where you have to measure the pressure. It could be absolute vacuum point where the pressure is equal to 0, okay. Theoretically it is a 0 pressures, you have a vacuum where the 0 pressure and you are measuring it, okay. That what will come a absolute pressures. That means you are absolute 0 pressure you are measuring it. But if you most of the case, as you know it, when you consider the fluid, all the fluid will have a surrounding of a part of atmospheres. Most of the cases what we consider in here, we are not solving the problems in a space or area, we are just solving the, or any other planets, we are just solving the very simplified problems in and around the earth. So, we consider the atmospheric pressure is the datum to measure the pressures. So, when you measure the atmospheric pressure is a datum, there is a two conditions it comes. One will be the pressure above the atmospheric pressure, another one will be the pressure below the atmospheric pressure. So, when you have the pressure above the atmospheric pressures, then we call the gauge pressures. That is that we differentiate between the local pressures and the absolute pressures. So, that is what will be the atmospheric pressures, and this atmospheric pressure can be measured with mercury barometers, okay. As you know it, it could be range from the 101.043 kilopascals, the pascal is Newton per millimeter squares. So, that what we measure it when you have a difference between P local and the P atmospheres, okay. That what P atmospheres, and here is also P atmospheres. When you have vacuum, that means it is a below than the atmospheric pressures. The reasons we will have a below than that what we P vacuums, that what will be below than these values, that what we measure it with respect to these ones. So, we can have a pressure measurements either from the vacuum or from the atmospheric pressure. If you need to compute it what will be the absolute pressure, then it is a very easy, you just use whether the gauge pressure or the vacuum pressures, that difference what we can get it, that what you just add with the atmospheric pressures to get the absolute pressure. There is nothing else where your datum is there, whether at the absolute levels or at the atmospheric level. Like many of the problems what you solve it, the fluids having a boundary at the atmospheric pressure levels. So, as that time we can measure the pressure difference between that, the positive side we call the gauge pressure and the negative side we call vacuum or the suction pressure, which is below than the atmospheric pressure. Never we go below the pressure equal to atmospheric absolute pressures, which is a 0 atmosphere or no pressure is there, which is at the vacuum levels. Now, as we derive pressure distribution equations which in vector forms, and let me simplify that equations which earlier we consider the acceleration due to gravity is a vectors which you should have a scalar component gx, gy, gz, and that what if you make it at the scalar level, as you can just split that equations, you will have a 3 equations. One will be the z direction, another will be the y direction, another will be the x direction. Just you are getting the component of minus of the pressure gradient is equal to the gravity component on that into the rho times, which is as equivalent to a unit weight on that directions. Similar way, this is the y directions and this is what the x directions. Now, if you align the gravity in one of the coordinate axis, most times that we do along the z directions. If it that the conditions, you can approximate this point all will be z0 will be the component, but other your gx and gy component becomes 0 because there is no gravity component, because that is what you consider along the z direction. The components in the x and y directions become 0. That is so you have a this is becomes 0. That means if you consider j is the vertical direction and x and y is on the surface. So, these equations what is indicated that in that case you will not have any pressure gradient. If I consider a horizontal plane, there will be no pressure gradient in x and y. So, there will be no pressure gradient, only the pressure will vary along the z direction. So, if you consider a horizontal plane, at that horizontal plane you will be pressure will be the constant. That what these equations indicate for us. Now, if you pressure only varies along the z directions, that means if I take from this point and if I just integrate this point, because pressures become now only a functions of z, okay. Pressure is only functions of the z, only in the vertical directions, and if I just integrated that P2 minus P1 minus rho gh z, okay. We remember we are considering z location from a particular levels. So, that negative component you will look it whether you are going up or the down, that is what the reference point what you will look it. So, if you look at that, if I am a z equal to 0 here and I am putting it the z value like this, the pressures, the P2 and pressure distributions will come a linear functions with respect to the z. So, pressure will vary, this is the free surface. At this point the pressure will be the atmospheric pressure, which most often we neglected that, which is very very less as compared to the liquid what we have generally we consider it, we neglect that pressure. Then after that we draw the pressure distributions, as it is a relative pressure difference is only a function of z of a linear functions only. So, we can have a linear variation of pressure from this free surface to this one, and that what we get it here, the linear variations of the pressure, and you can look it that what is a unit add weight into the z value, that what the pressure is. It is a very simplified things, okay, we have derived it, but if I consider the very simplified the concept of virtual fluid balls, we have derived the equations very complex way vectorically, then followed simplified it, then what we got it, the pressure does not varies along a horizontal plane, only the pressure varies only in the z directions, and that the pressure variations is a linear functions with respect to the z. But if you consider the virtual fluid ball concept, that means I have a conditions where the balls are as equivalent at the rest conditions, and pressure let be acting on this P atmosphere. Okay. I want to know it what will be pressure at this point, let be the P2, nothing else. This pressure will be the, because of this atmosphere pressure, if I make it 0, then what will be this? It is a weight of whatever the weight of the liquid, that what will be the pressure on this, weight of the liquid divided by area, surface area. If I consider the unit surface area, that means unit weight of the waters or multiplied by the z, that what will give a pressure to this. That means I will have pressure will be rho g, weight of the water or weight of the virtual fluid balls whatever stacking here, into z, the column height. So, this is a very simple way we can find out. If you are having a problems now or not getting the equations, which are very simple equations, you can just think it that we have just stacking of the fluid balls, virtual balls, and just find out what will be the weight acting on a unit surface area, and that what will the pressure is going to act it. Just weight of the fluid balls and divide by the area, that what will you give it. The weight will be the unit weight multiplied with the elevations z into the area, as we consider area is equal to 1. So, rho g h, that is the very simple things we can, as the z varies,
the pressure distributions varies linearly. That the simple way, if you consider virtual fluid balls, not bothering much about whether is what type of equations, how the vertically we are simplified for the z directions. If you have the fluid at rest conditions, just take the control volume, just consider the virtual fluid balls all are in the rest, and this virtual fluid ball can have a different way. So, let me explain that considering a simple examples here, very interesting examples what we have considered it here, like you have high altitude lake, okay, and that what is connected through a tunnel of a reservoir and the dam you have. There is a winter snow cover will be there, and the summer there is no snow cover. We want to find out what could be the pressure is going to act on the P, A, B, C, D, E and F. This is the locations we can consider a horizontal surface. As we have know it that along the horizontal surface the pressure will be the same when the fluid at the rest. Otherwise fluid could not be rest if there will be the pressure difference. That what the fluid will start motioning. So, any horizontal surface if you consider it when the fluid is at rest, the pressure on that horizontal surface becomes equal. So, that means in mathematically that will be PA, PB, PC, PD all will be the equal whatever way the as the connected surface. It may happen it similar way if I take a 1, 2, 3, 4, 5, 6 which are lying on a horizontal surface, you can consider pressure will be the equal each other. That is the pressure will be the equal. So, P1, P2, P3, P4 will be equal. Let us consider there is the in a winter seasons there are a lot of snow formations here, okay, lot of snow formations here, okay, additional the snow is here. If we again you consider the pressures along this P and PB, P, C, D, E, F, you will have a same pressure. There is no doubt there will be adjustment of the water levels because of this change of here as it is connected through the tunnels, but the pressure of any horizontal surface will be the same. So, either you have a snow cover or no snow cover, it does not matter it, as the fluid is at rest and it has a connected through a tunnel, when is a fluid is at rest, the basic general philosophy is here, along any horizontal surface you will have the pressures is equal, as the pressure does not vary along the x and y directions, only pressure vary along the z direction. As the snow formations happens here, that what will adjust the water level from these two in the reservoir such a way that any horizontal surface if you consider it, you will have the pressure difference will be the same. Similar way, if we are adding a different fluid, let me consider we are adding a different fluid with a different density, not the water here, water plus another density of water, low density water where fluids we are adding to that, definitely it will have a response to here. So, when you have any connected systems, fluid is a rest conditions, you take a horizontal surface, on that horizontal surface the pressure is equal. As any connected system is going to change in one part, that what is going to reflect in other part. That what I try to say, that if something happened to this lake, it affects to this reservoir. Still it rests to the rest condition. Still these coming to a conditions where you will have the pressures along the horizontal surface should be equal, that the conditions prevail. Either it is a snow formations or adding more water, or different liquid with a different patterns, that what is reflected here, that what will be reflected here. So, these are very simple conditions what we are talking about, very complex problem. If your fluid is in static conditions, we can simplify that problems as if it is a connected through the tunnels or through any tubes, okay, that is what we will discuss in manometers. We can consider any horizontal surface, and that horizontal surface as it indicates is that the pressure is equal, pressures are the equal over that surface. That is the conditions we consider to solve many fluid flow problems in a hydrostatic And second thing is that you can easily know it if I consider A and 1 point, definitely the pressure at the 1 should equal more than pressure at the A, because if you consider the virtual fluid bulbs also, the weight of the water and weight of the waters here, that what is different. The more water, weight of water is holding per unit area at the A as compared to these ones. So, pressure at the 1 will be more than this, or as you go deeper and deeper, you will have a linearly proportional more pressures you will get it. That is what very basic things, that as you go more deeper and deeper, the Z is more, the depth is more, the weight is more, and you will have a more pressure, and the pressure is here a linear functions in a Z direction, and pressure does not vary in a X and Y directions, as it becomes constant. This is the very simplified we consider when the fluid at a rest conditions, like these lake problems which is connected to a reservoir. Now, let me consider the capillarity effect. As you could have seen some of the books, even if the class 12th levels, what we do it, we just summing the two force components, the force due to the surface tensions and the gravity force of the capillary part. You know it, what is the capillary? That means if you use a small tube and insert it into a fluid, you can see there is a rise of water or the fall of mercury, that what you can observe it, and that height is called capillarity height. That what is here, we have a water and a small tube, glass tubes, if you inserted it, which you can visualize that the water will go into that. This is what the capillary effect. Now, in this lecture, what I am talking about, that let us consider a control volume and solve the problems. Okay, that was my point. Let us consider a control volume and solve this capillarity problem, which is a very simplified problem, because here these two force components works. One is the gravity force, another is the surface tension force. These two force components works. Now, if I consider this is the control volume, that means I have considered this part as a control volume. Okay. This is what the surface tension, and theta c will be angle of contact. As I say that pressure will have a linear variations. So, you can have a pressure will be linear variations, pressure will be the linear variation. But when I consider this hydrostatic distributions, the point at 1 which is inside and the point 2 which is the outside, since I have considered a horizontal surface, at the second point the pressure is equal to pressure atmosphere. The definitely point which is inside the tube, also the pressure will be the atmospheric pressure. That is what the conditions. Since we consider the fluid is a rest, if I take a horizontal surface which is just matching with the free surface of water and air, where the pressure is acting as atmospheric pressure. So, inside the tube also in that horizontal surface pressure will be atmospheric pressure. So, my control here I have the pressure which is equal to atmospheric pressure. At the top, as water and the air is there, we will have a atmospheric pressure. So, at the top you have atmospheric pressure, below you have atmospheric pressure, and over this control surface, with a radial control surface, you will have a pressure distributions will be the hydrostatic pressure distribution starting from 0 to the at the jet level. And what the force component is acting? Weight of this part plus counterweight by the surface tension force, nothing else. Because we are looking the force component along these z directions, along these directions only in this direction. So, weight will commit, that what is counterbalanced by the force due to the surface tension. So, upward force due to surface tension you can find out, that is what the surface tension component in the z directions into phi into d, as you know it, the circumferential length, circumference of this tube, that what the surface tension multiplied with the length where it acts it, that component we got it. Weight of the fluid, you can get it very easy, is that unit weight multiplied with the volume, that what is the area into the height of these ones. So, you have a weight of the fluid. just equate these two parts, the upward force due to the surface tension and weight of the fluid. What will get it? H will be this part, okay, as a functions of surface tension, d is a diameter of the tube, theta c is a contact angles, we are getting this value. So, the capillarity, if you can see that, it is a proportionality to the surface tension. Here we are talking about water and air and the glass. If you have used different fluid conditions, interactions conditions, you will have a different surface tension, also the contact angles, and the d, which is a inversely proportional. That means, if I make a smaller diameter of capillary tubes, I will have a more height rise. That is what it happens. As the d's become smaller and smaller, h will be the more and more. Okay. So, that is the conditions which prevails it, and this the surface tension and theta c, it depends upon the fluid contact with another fluid, maybe water, maybe other things, and the solid surface here is the glass. So, surface tensions and the theta c depends upon the where the interactions happening it, and d is the diameter of the tube, the capillary tube what you use it, which is that. As the diameter of capillary tube will become smaller, definitely h is increases at that. Here we have considered the control volume to solve the problems, to define you how the pressure distribution is happening it, how I am equating all these force components. No doubt I have neglected, I have tactically I use it only the force component equating along these z directions, which is very easy for me to just look in the z direction because other forces balanced each other. That is what I am not worried about that. More things what I am looking at, that as I consider a horizontal surface just connected at the atmospheric, fluid is at rest. So, any fluid inside the tube also will have the atmospheric pressure. That is what the major conditions we have considered it. That is what we have. So, but you cannot consider any point above of that and equate it. You cannot do it that, because the pressure acting on this point is not equal to the atmospheric pressure. There is no liquid connected on that. So, that will be the difference. But when you have a common fluid is connected to the surface and you take that horizontal surface, and that horizontal surface definitely will have the atmospheric pressures what is acting there, that what will be the atmospheric pressure inside the capillary tube. So, that the things what I just repeat you to look at the control volume approach, which is we can easily solve, or very complex problems also you can solve it if you follow control volume approach as compared to the just simply balancing force component what we generally do in other cases. But my point is here, please look at the control volume level, draw the pressure diagrams on the control surface, equate the force components, then you solve the problems, which is much more a systematical approach to solve the problem as compared to just equate the force without drawing the control volume, without drawing the control surface, without drawing the pressure diagrams and solving these things. That please do not follow that ones, which is sometimes it will be very difficult when you have a very really complex problems, not the academic problems what we do it on this thing. Now, let me come it to the mercury barometer case, which is a very simplified same capillarity concept what used to measure the atmospheric pressures. Here we use the mercury and just insert a tube such a way that the tube should contain the vacuum. So, we can have a systems to remove the air and to have the vacuum, and you just inserted in that tube on that one. Same concept again is coming it. Here the P1 will be the 0 because this case is the vacuum. Same capillarity effects, nothing else, and same control volume concept we will use it to solve the problems. Here if I consider the point as the surface, I will have atmospheric pressure here, also will have a P2 is atmospheric pressure as here this thing. So, again I will wait the same way. If I do the derive control volumes and all, I will get it, the height will be P atmospherics divided by the unit weight of the mercury. So, if I know the height, I can compute what will be the atmospheric pressure. This is what use very simplified concept for mercury barometers. Just measure the height with a graduated scale. As you know the height, you know the unit weight of the mercury, so you can compute it will be the atmospheric pressure. As you know it, you go for higher altitudes like go to top of the Himalayas, definitely the atmospheric pressure is less, and that is the reasons you feel dizziness when you go for the higher altitudes, and there are other problems will cause it when you go for the higher altitude. Because of that, many army problems, when army goes to higher altitudes, they go step by step, they stay for a different altitudes, then accustamize with that pressures, then they go for the higher altitudes. As we know it, we go for a higher altitudes, your pressure decreases, and that is to ameliorate it and customize with that pressure difference. Army when moves from the lower altitude to higher altitudes, it goes phase wise. With like for examples, if somebody goes to the higher altitudes like a Himalayas, which is as on average is 5,000 meter above the sea. So, phase wise you go it first 2,000 meter above the mean sea level, 3,000 meter above the mean sea level, then we go for 4,000 meter above the mean sea level, so that the body customized, the army's person's soldiers body customized at the different level, and he can that the low pressure zones at the high altitudes he can take care of when you go for the higher altitudes. So, and that is the reasons we measure the atmospheric pressures and the different, and that what we can use is mercury barometers. Nowadays there are the electronics versions of pressure measurement device are available, but mercury barometers works in a very simple concept using the capillarity concept only. Here we use the mercury, as you know it, the unit weight is much larger, 13.6 times than the water. So, H becomes lesser, so we can measure the height and we can find out what will be the atmospheric pressure. With this note, let me summarize today's lectures, that we started with the examples of gravity dam and liquid working as a rigid body motions, which we will discuss much later more that. Again, I have to highlight is we use the Taylor series expressions for approximating any continuous functions like pressures, velocity, density and temperature. And that is what is necessary when you use a control volume which becomes infinitely small, delta x, delta y, delta z, then you consider what could be the pressure distributions. If your pressure P is at the centroid, what would be the pressure at the different surface? And as you know the pressure distribution, and just equate the force component to get the equation. That's all. It's not a big things. So basically we look at that, then we discuss about the what is the datum we consider it to measure the pressure, whether the pressure from vacuum levels or the pressure from the atmospheric level. So that atmospheric pressure or the vacuum pressures, what you consider it. Hydrostatic distributions we discuss it, the barometer and the capillarity height, how to deduce that, what we discuss it. And as you is, again I can repeat it, that the pressure is becomes a scalar quantity, as it does not have a direction. So that means the any point if you consider it, pressure can be considered is over that is normal to that. That the concept we will use it later on, and you also know this capillarity. With this I conclude this lecture.